Good morning, everyone. So today we'll go on with chapter 8 about the potential energy. And as we can see from the title, so we're going to discuss in this chapter a new type of energy. We have seen already in chapter 7 the first type of energy, which we discussed, and it was the kinetic energy. And we said that the kinetic energy is related to the motion of the object in the speed. So in other words, the kinetic energy is related or is proportional to the speed squared of a given object. And whenever an object is moving or it has a speed, then we can define a kinetic energy. But this is not the only energy that exists for a given object or for a given system. We can have another form of the energy, and one of these forms is the potential energy. So when you have a system on which you have many forces or a given net force acting, and this force does not change the kinetic energy of the system, then we know that the work done by this force should appear in another form of energy storage that we call potential energy. يعني طالما نحن في عنا force عم تعمل action على السيستم and there is a work behind this this action, مثل ما نحن بنقيس يعني قد ايه efficient is a force in producing a motion, then there should be another form of energy storage اللي هي بنسميها potential energy. And in our course we're going to explicitly study two types of potential energy. The first one is the gravitational potential energy, and the second one is the elastic potential energy. So let's start for the first type of energy اللي هو gravitational potential energy. So as the name can immediately indicate that this potential energy is related to the gravity, to the force of the gravity. Let's derive an expression for this gravitational potential energy. So for this reason, let's consider that we have an object. So this object is attached to some cable, and the cable is attached to some motor, so that the motor is pulling up this object at a constant speed from a given initial position to a given final position, from y initial to y final. And so it's done by an external agent. This is why let's call F up, to say that this is the F applied, the force applied. This is the force applied by an external agent, which is lifting up this object slowly in such a way that its speed remains constant from an initial height y initial to a final height y final. So the point now is to determine the work done by this force exerted by an external agent on this object. According to the definition of the work is defined as the scalar product between the applied force and the displacement. The applied force is constant, so actually we can use the expression of the work for a constant force, and so this is nothing else than the scalar product between F and delta R. Now, how much is F applied? Okay, we don't know how much is F applied. However, we can deduce it from the Newton's second law. What does it tell us, Newton's second law? It tells us that the sum of external forces is equal to MA. مجموع الفورس that act on this object, they determine its acceleration. What are the forces acting on this object? So we have F applied on top, and we have, so pulling the object up, and mg, which is pushing the object down. Since the object is moving very slowly, so there is no acceleration, that means that this is equal to 0, the summation of the forces. And so the modulus of F applied is equal to the modulus of the weight of the object. So we know now how much is F applied. It's given by mg. And if we just replace or substitute each term by its expression in the scalar product, we end up with F applied along the vertical direction dot delta y along the vertical direction as well. And so this ends up in m times g times delta y, where delta y is y final minus y initial. So we end up with the expression for the work done by the external agent to lift up this object from y initial to y final as mg y final minus mg y initial. So as you can see in here, the expression for the work is a difference, is a subtraction between two values. Each value, it corresponds to the quantity m times g times y evaluated at a given time, right? So it's mgy evaluated at t final minus mgy evaluated at t initial. And so actually, since the work done by a force is interpreted as a transfer of energy, whether from the system or to the system, then we can define this quantity here, mgy, as an energy, and this energy is related basically to the gravitational force, because F applied is in magnitude equal to the gravitational force. And so we can identify the gravitational potential energy as the product between the mass times g times y, where y is the elevation of the object at a given time. So the work done by the external force by F applied is given by W equals to delta UG. By UG we mean the gravitational potential energy. ومنحط G لحتى نقول إنه هي gravitational. So this is why how we differ between, we distinguish يعني between the gravitational potential energy and the elastic potential energy. Now, if you do exactly the same exercise, but taking instead of the gravitational potential energy, if you take a spring and you try to pull the spring, for example, by a given elongation x, and you apply a given force F applied onto your system. So if you consider a system, a given system, you have this way. So you have a block, for example, and this block is attached to a given spring, okay? And then you push, you compress the, so you push the block leftward, and this compresses the spring by a given amount delta x. So after you do so, the block will be subject to Fs, which is, we call it Fs to say it's F spring, which is given by, again, just to remind you that Fs is given by k times x if you pull this object by a given x, right? And so if you do so, if you do the same exercise as in here, you will see that you will end up with an expression for the elastic potential energy given by EU elastic is equal to half times k times x squared. And so from here we can say that usually we don't use U elastic, but we use the term US to say it's the potential energy related to the spring force. And so we end up with US equals to half kx squared. So this is the second type of energy that we are going to deal with, اللي هي elastic potential energy. Now, how can we go, or how can we define what we call the mechanical energy? Let's see. So in this section, in this next section, we are going to discuss the mechanical energy. So again, if you take the same example as before, so you lift up this object by a given height from y initial to y final, and then at some point you don't apply any longer F external force, اللي هي F applied. In this case, the object will fall back to its original height under the action of mg only. So بهالحالة الobject بيصير under the action of the gravitational force, and so under the action of the gravitational force, it will fall down from y final, to y initial again, right? Let's see what happens, and let's see how can we describe the motion of this object from these two or between these two positions. From the work kinetic energy theorem, we know that the net work done on the system, it's given by the variation of the kinetic energy. So we know that W net is equal to delta K on one side. On the other side, how much is W net? We know that W net is equal to WmG in this case, because the only force that is acting on the object is the gravitational force. But the gravitational force is constant because we always assume that we are near the surface of the Earth. And as you know, إذا كنا قراب من سطح الأرض, the gravitational acceleration اللي هي G does not vary as a function of the attitude. That means that mg is constant, and so we can use the expression for the work done by a constant force to determine the work done by mg. So this is why it's nothing else than the scalar product between mg and delta r. So let's write each vector in terms of its unit vector. mg is along the vertical, so it's mg times j اللي هي اخذنا الواي axis pointing downward دوت الدلتا ار هي بهالحاله صارت الفاينل ماينس الانيشال، ما انه نحن رايحين بنزول، فاذا هلا الفاينل صارت واي انيشال والinitial صارت y final. So this is why we say dot y initial minus y final along the vertical direction. And if you just make an expansion هون ال g or j dot j بتكون equal لواحد لأنه ال j is a unit vector. So the scalar product of a unit vector هيدا هو معناتها nothing else than j squared لأن المودulus of j, and this is nothing else than 1. And so we end up with mgy initial minus mgy final. So which is ug initial minus ug final. So first of all, from here we can deduce that the work done by the gravitational force is equal to minus delta ug. Okay, and when we say minus delta ug, we always refer to delta ug as the difference between the final minus the initial. يعني لما نحكي عن دلتا، لما يكون في دلتا مع الفاريبل او البارامتر whatever شو ما كان، بنكون على طول عم نحكي عن its difference ما بين الفاينل والانيشال. فور اكزامبل لما نقول دلتا كي هون على طول بنعني فيها كي فاينل minus كي انيشال. دلتا هي على طول between final the subtraction of the final minus the initial. So we can deduce finally that the work done by the gravitational force is equal to minus delta ug. And actually this is the case for all the forces which are associated with a potential energy. يعني حتى إذا بنروح بنجيب the work done by the spring force, you will see that this is nothing else than half kx initial squared minus half k minus half k x final squared. And this is what we did in the last chapter. So if we define half kx squared as the elastic potential energy, you'll see that this is nothing else than usi minus us final. So this is nothing else than minus us final minus us initial اللي هي delta u. So this is nothing else than minus delta u spring. So you have to keep in mind this kind of relations. The work done by the gravitational force is equal to minus delta u g. So it's the difference in the potential energy with a minus sign on the left-hand side. And in the same way, the work done by the spring force is equal to minus delta us, where us is the elastic potential energy. طيب هلا كان هدف الاكسرسايز هون نحن مش انه نوصل لهون، هيدا بس كان كومنت على جنب. نحن شو كان هدفنا؟ كنا عم نعمل استدي للموشن لهالاوبجكت بعد ما هو نزل، بعد ما فلتناه، يعني بدون ما يكون في عليه اكشن من الاف ابلايد. طيب جبنا الدبليو نت، فاذا دبليو نت هي ماينس دلتا يو جي، بنحطها بقيمتها فوق، بصير في عنا if you just take equation 1 and 2 you'll end up with delta u is equal to minus delta ug, which bring us to the following relation: delta k plus delta ug is equal to 0. So what does it mean? That it means k final minus k initial is equal to u initial minus u final. So هيدي احدى الاشكال هي ان نكتبها بهالطريقه، واذا نجي بنفصلها بيطلع معنا انه k initial plus u initial is equal to k final plus u final. And so this is what we call the principle of conservation of mechanical energy for an isolated system. So here we define the summation of both kinetic energy and potential energy. We define this sum to be the mechanical energy. And so this mechanical energy, it includes k and plus ug. Now, in the general case, the potential energy term does not only include the gravitational potential energy, but it also includes the elastic potential energy. يعني لما نحكي عن mechanical energy, we can generalize this equation, and so we can say that the mechanical energy, it's defined by the kinetic energy plus the potential energy coming from the gravitational force plus the potential energy originated by the spring force أو اللي هي elastic. So ما بنحط كل مرة هيدا الترم، بنحطه مباشرة. It's the kinetic energy K plus the plus the potential energy U. وهيدي ال U it includes both gravitational and elastic. So لما نحكي عن mechanical energy هيدي ال U بتتضمن اثنين، الجرافيتيشنال والالاستيك. طبعا اذا كان بالبروبلم او بالسيتويشن اللي عم ندرسها في سبرينج بيكون في elastic potential energy. اذا ما كان في سبرينج عموما ما بيكون في elastic potential energy، لانه معظم الحالات اللي نحن او كل الحالات اللي بنتعاطى معها اذا ما كان في عندنا سبرينج بيكون في عندنا كورد، بس الكورد عموما ما بيكونوا elastic. So in principle whenever you have a spring you have an elastic potential energy. So this is number one. Number two, the takeaway message, in other words, mechanical energy for an isolated system is conserved. That means that the summation of the kinetic energy and the potential energy remains constant. شو بيعني هيدا الشيء؟ يعني إنه إذا كان في عنا isolated system، يعني a system that has no interaction at all with the environment, with the external surrounding, then there could be a variation in the kinetic energy of the system. However, this variation will show up as an increase or a decrease in the potential energy of the system. يعني عمليا هون أي تغير بالkinetic energy هو عمليا بنقشعه as energy storage، حيتحول لenergy مخزنة بالجسم، سواء كانت على شكل الجرافيتيشنال بوتنشال انرجي او بشكل الالاستيك بوتنشال انرجي. as an example انه انتم لما تضغطوا رسور وتعملوا له كومبريشن، عمليا انتم اللي عم تعملوه انه عم تخزنوا فيه الاستيك بوتنشال انرجي. لهالسبب لما تشيلوا ايدكم اذا كان في بلوك على الانف، البلوك بيمشي بسرعه معينه، علما انه بيكون ثابت لما تكون بعده الرسور compressed. فبالتالي this is what we mean by the summation of kinetic energy and potential energy remains constant. Okay, so this is it for this